Okay, hello and welcome to a new week. We're going to start this set of slides about functions and relations. It's going to be very fun. Okay, so let us get started with functions. And if you've taken like a calculus class, this is all going to be very, very familiar. It's just we're using f's instead of like y equals all this other stuff, right? We're giving names to our things, and this is the mathematical kind of function. And we can compose functions. First we do g, then we do f, or first we do f and then we do g, and we can get different things based on that. I don't really agree with these pictures, but there is a difference, and at least it demonstrates that. We'll get to all of that. Okay, so let us begin. Let us formally define what it means to be a function. So a function has a name. We'll call our example function f, and it maps things. It's like your unordered map or your map in C++. It's taken stuff from one set x, could be anything, right, to something of another set. It could be the same one if it wanted to. And I want to prove to you that that is just a subset of x cross y. So let's say this. Here is my set x. Here is my set y. They're little clouds or maybe ovals. Maybe x has 3 things, and y has, I don't know, who knows, 4 things. These little dots are the elements inside of those sets. So maybe x takes this dot to this one, and this dot to this one, and maybe this dot all the way down here. Yeah? That is all that you need to specify a function. You just have to say which elements of the x set get mapped to which elements of the y set. And if I were to give these names, like x1, x2, x3, y1, y2, y3, y4, notice that all you need to specify completely what a function does is elements of this x cross y set, this Cartesian product, because remember that elements of that are just pairs. They are pairs of one thing in x and another thing in y. So this function, let's call it f. F is doing all these things. F equals, in a mathematical sense now we know how to define it, f equals the set of all these pairs, x, y, for all the things that the function is taking to different places and where it goes. So it's hard to explain in words. Let me just write it. So f, the function, is equal to this, x1, comma, y2. That's the first element of the function because it's taking x1 and mapping it to y2. Yeah? That's the idea. And then the next element of the function f is x2 mapping to y1. You see that? And then x3 mapping to y4. That is the idea. That is the function. You can define a function like this. It's just a subset of x cross y. And remember, the whole thing is all the different pairs, like x1, y1, x1, y2, x2, y1, all those things. We are taking a subset of that Cartesian product, just picking out the stuff that is part of the function. All of the x values and what they're getting mapped to by f itself. Okay? So hopefully that's making some sense. Please yell at me if it's not. This is the idea. We can define a function this way. We now have enough tools to do it. And I think this is very, very different to how we've done it in a math class before, right? But this is the formal way. This is how we do it. So, yeah, the idea is for every x and x in this domain set, we'll get to that later, just another bullet, there is exactly one y and y, okay, for which x, y is in f, because f is just a set. You see that? It's weird notation, but it's true now, because f is just a set. It's a set of Cartesian, well, it's a Cartesian product set. It's a set of pairs. First things in x, next things in y. Okay? So it's just saying this particular x is getting mapped to this particular y. That's the point. x1's getting mapped to y2 and nowhere else. We don't have this exactly one condition is telling us that we cannot have this. This is not allowed. You see that? That's the idea. Bad function f. You can't have it like that. A function must take an x to exactly one y. Okay, that's very, very important. Otherwise, it's not a function. Okay, we say it's not well defined. We'll get to that in just another bullet or so. Okay, so x, we call it the domain. Yeah. So maybe I should use colors. So x is the domain. Yeah, go away, please. Okay, and y is called the target or the codomain. Okay, either one. You can call it that. It is not the range. Okay, you might have heard that term before, but it's not the same. So, dun dun dun. Yeah, so x is the domain. It's the thing that you're giving to the function to take you to the next place. Okay, you give me an x, I give you a y. That's what f is trying to do. So it's taking an element of the domain and mapping it to exactly one element of the codomain, exactly one element of the target. Those are the same word. Okay, those are synonyms. So yeah, a function is just a set of pairs. Now I think we're very well acquainted with that fact. Okay, and things could go wrong. Okay, I showed you one way. Let's talk about it. So f needs to map, first of all, an element of the domain to at least one, or sorry, exactly one thing. Yeah, exactly one. So if there was an extra x and it was not mapped to a y, like if we had an x4 and it just wasn't part of the function, this was x4 right here, and it just wasn't part of the function, then it's not a function anymore. It has to take every element of the domain somewhere. Okay, you can't just miss an arrow. It's impossible. You got to take everybody over here somewhere else. Okay, you don't have to hit everyone over here, but you have to take everyone over here. I hope that's making sense. Okay, so if the function took 0 elements, if the function took an element of the domain to 0 elements of the target, then it's not well defined. Or if it took it to more than one element of the target, then it's also not well defined. You have to map exactly one. Okay, so this is wrong. Map in 2 places, or forgetting an x4. That's also wrong. Okay, that's it's called not well defined. A function is well defined if this is true. All right. Okay, so you may have heard the range. Maybe I should make that bold. Oh, maybe that's why I didn't make it bold. There we go. Oh, now it's ugly. I'm sorry. We're just gonna have to live with it. All right. So the range of f, it is the set of all y's that are mapped to. Okay. So notice that the range is different from the target / codomain. Y is this whole set. Oh no. Y is the whole set, y1, y2, y3, and y4. This is the whole set y. But notice that the function isn't mapping x's to every element of y. There's not enough. Yeah? So that's our third term. That's our last term that you might have heard of before. The range is, well, it's defined to be like this. And I read it to you in math. Let me just explain it to you in English. It's all the y's that are mapped to by some x. Okay? You see that? So there's like a there exists hidden away in here. So the range of this function f is y1, y2, and y4. Okay? Which is different to the codomain. It's not equal to the codomain. Sometimes it is, doesn't have to be. Okay? So I just spent a lot of time on this slide, but it's very important. Okay? I hope it's making some sense. These are functions. All right. And now on to one last term, but before that, an example. So let's pretend we have a function that's actually taking sets we know about already. It's taking integers to integers, and what it's doing is it's taking the absolute value. So f of x equals the absolute value of x. So let's talk about this. So f of like -42 is getting mapped to +42, and then f of 3 is mapped to 3, f of 0 is mapped to 0, etc., etc. I hope you see the idea. So what is the domain of this function? Yeah? What is it? Well, we can just look right here and see immediately that it is the set z, but this is the integer set, so we got to be pretty. That kind of set. Okay, the target is also z. Yeah, it's taking integers to integers. Totally fine. But now is where the fun part happens. The range, I have warned you, is not necessarily the target, is not necessarily the codomain. What is it? So the range, we need to think about this. Like, let's take f, and well, it's mapping elements of the number line. So here's 0. It's mapping elements of the number line to places, yeah? On the number line again. So integers, it's mapping 1 to 1, 2 to 2, -1 to 1, -2 to 2. You see that? It's jumping everybody over to this side. That is the key. Okay, so that is how we notice that the range is not the same as the target. The range is all of the non-zero, all of the non-negative elements of Z. So we can say that it is the natural numbers. You see that? It's beautiful. So that is the range. Okay, so hopefully that was fun. And now we have one last term, for now at least, functional equality. So we can say that two functions are equal under some very specific conditions. Okay, they have to have the same domain and target. That is required. Even if they do the same thing, if f was defined on R to R, it would be a different function, like g on R to R, where g of x equals the absolute value of x. Because now g's taken things like -3.14 to 3.14. It's not at all the same. So that's why we kind of require this. They have to have the same domain and target. Even we could have the same function and make it R instead. It would be a different function. Okay? That's required. And yeah, so that's the first thing that you need to make sure is the same. And then you need to go and check every element. So if f of x ever differs from g of x, then they're not equal. Okay, so to be equal on the function level, you have to have the same domain and target. That's required. And also, for each element of the domain, you take it, map it by both functions, and make sure that the result is still the same. That hopefully makes sense. Like, yeah, they otherwise wouldn't be equal if they didn't agree. Yeah, so that's called functional equality. Okay, so that's just another term. This makes sense. Just watch out for this. Yeah. Okay, your turn. So here's a diagram. And I want you to think of, or give me some pairs back, what are the domain and range of the functions f and g. Okay, so give that a try, and I will be right here. So let me make sure I'm actually recording, yes. So hopefully you gave this a very nice try, and let's, I guess let's do f first. So here is, the domain. Here is the target, the codomain, but not the range, not necessarily the range, yeah? So let's talk about this. So for f, let's do f over here, g over here. We have domain. Actually, let's do g underneath in a second. Domain, well, that would be the set of all things that are getting mapped, yeah? So it's a, b, c, d. And then the target, the range, is all the things that are being mapped from somewhere. So that happens to be everybody here, because it looks like everybody's getting mapped somewhere. Yeah? So that is the idea. The range would be W, X, Y, and Z. Another question is, are they well defined? And the answer, at least for the first one, is absolutely not, because this is being taken two places. Can't have that. Gotta get rid of one. Okay, and then for G, let's do G over here. We have the domain. It's all the stuff that's getting mapped over on this side, all the things that have arrows coming out of them. So we have A, B, C, and D again. Yeah. And then the range is all the things that have an arrow going to them. So it's only three things this time. You see that? W, X, and Z. And now the question is this well defined? So, are all of these being taken to exactly one place? And the answer is yes. The answer is yes. So, it is in fact well defined. Weird, huh? So that is the idea. It is well defined. This might look weird, but it's okay. Just like the absolute value took negative 42 to the same place that it took positive 42. That's okay. It's okay to double up on the range, on the codomain. Can't double up on the domain. Yeah? So, hopefully that's making some sense. And let us move on. So another example for you. So I want you to discover, figure out if f is equal to g. So I've defined f to be this and g to be this. They involve absolute values. Tell me if f equals g. Okay? So to determine this, we should maybe go back to our definition. They have to have the same domain and target, first of all. Do they? Yes, it looks like these are the domains, these are the codomains, they check out. Perfect, check. All right, now we need to make sure that for every element of the domain, the functions agree. Okay, so now we need to put our thinking caps on because this is going to be interesting. And I think you might notice that it's possible to make a counterexample. Okay, so let's pretend, let's take f of, I don't know, 2, negative 2, and g of 2, negative 2. And we need to make sure that they're the same. Okay, we need to make sure that those are equal to each other. But f of 2, negative 2 is the absolute value of 2 minus 2, which equals the absolute value of 0, which is equal to 0. And then this one is the absolute value of 2 plus the absolute value of negative 2, which is 4. Ooh, those are not equal. Okay, then the functions agree is the next requirement. But oh man, are they arguing? So the answer is no. Okay, so hopefully you got that. That is a fun one. We notice that we can have fancy looking domains, okay? And these are just multi-argument functions, yeah? Not too bad. So now we have new topics. Are you ready? So we have things called floor and ceiling. So there is a function called floor, and you actually kind of know it already because it's like the way that doubles are getting converted if you ever converted them to an int in C++. So the floor function, it looks like this. It's like you're drawing absolute value almost, but then you're also drawing the ground because that's the floor, right? So the floor of a number, it looks like this. You say the absolute value of the number like that. But then you add these little floor lines. So that's the notation for floor. It takes a real number, so a number with decimals, and it chops off some decimals somehow, okay? It doesn't round, it does the floor operation, okay? It maps a real number to the nearest integer in the downward direction. It's always going down. So you can think of these like arrows, like gravity is pulling it downwards. Okay, that's the floor function. So it's the largest integer that is less than, largest integer y that is less than or equal to the original x. Okay? And so this is the notation. Weird looking, but you'll know it forever now. So 3.14, the floor of that, we gotta find the nearest integer in the downward direction. That is just 3. You see that? Totally possible. All right, so 42.5, what do you think? It's not rounding. We're still going down. It's 42. See that? So it's as if you were static casting. To an int of like 3.14. It's exactly what's happening. Or 42.5. It's exactly what's happening. So you might want to think of it like that. Okay, 394. We've got to find the closest integer that's less than or equal to it. Oh, we're already at an integer. We're good. 394. Yeah, not too bad. And then we have the opposite. We have the ceiling function, because we have a house metaphor for some reason going on. So it looks like this. You draw your little absolute value lines, but also you draw the ceiling of the house that the number is staying in. Okay, and we're pretending that gravity got shifted, and we're finding the nearest integer in the upward direction now. Okay, that's what the ceiling does. So it's again taking real numbers to integers, but the way it's calculating the integer to go to is different. So the ceiling of a number x, of a real number x, is the smallest integer y, such that y is greater than x this time. Yeah? That is the idea. All right? So the notation is kind of the opposite. It is We can call it the dual if we wanted to. So we are going up now. We're taking the elevator. So 3.14, the ceiling of that, what do we think that is? Well, it's going to be 4. You see that? That's the closest integer that is bigger. Yeah? Bigger or equal to. So then 42.5. Now we're actually kind of rounding it, but it's a trick because it doesn't always round, right? Now we're going to 43. 43. And then 394. Again, it's already an integer. The closest integer that is greater than or equal to the original real number. It's still the number, 394. Yeah? So, that's floor and ceiling. It is useful to talk about programming with floor. Ceiling is also nice sometimes. Okay? So, as computer scientists, we kind of like floor a whole lot. Okay, so you'll get used to that one maybe a bit more. So here is a question for you. And because it's after this slide, you might need to use this. Let's talk about it and then have you answer it. Okay, so a baker is packaging goods for sale in boxes of 8. He has Y cookies. We don't know how many, but it's a number. Y cookies. It's an integer, we would hope. Actually, it would be a natural number, we would hope, right? To put in the boxes. And how many boxes we want to know can he possibly sell? We don't know how many cookies he has, but we want to figure out how many boxes of 8 cookies he could possibly sell with Y. Y cookies total. Okay, so I want you to write your answer in terms of floor or ceiling. Okay, think about this. So, what are we going to do? So let's do some examples. It's always good to do examples. So let's pretend that the baker had like 24 cookies. Then for sure he's putting 8 cookies in a box, and we have 24. That goes in cleanly, so he's making 3 boxes, right? 3 boxes, none left over. We are golden. That was the right number of cookies to make. What if, though? What if the baker had 25 cookies? What if Y equaled 25? What then? Well, he is forced to do boxes of 8. I don't know. Maybe that's the special that's going on in his bakery. He's going to have a cookie left over, right? He can only still make 3 boxes. Ooh, you see where I'm going with this? So we're kind of forced to move down. Yeah? There's a division happening, and we're forced to move down. Do you see that? So how many boxes can he sell, given Y cookies? Well, it's Y over 8, right? But if he had any left over, any decimal places, he doesn't have enough to make another box. Do you see that? So it's got to be floor. It's not ceiling. It's got to be floor here because we got to chop off the decimal places. We don't care if he had, we don't care if Y over 8 was, like, with 1,000,000 cookies, it was, I don't know, like 1,000.99999. There are not enough to make another box. Okay? So we have to use floor. Can only make 1,000 boxes. Yeah? Hopefully that makes sense. Oh no. So that is using floor in real life. Yeah? We use it all the time, but we don't think about it, and now we have notation for it. Okay? So those are a bunch of definitions, and we got practice with those. Now let's talk about the kinds of ways or properties we could have on a function. Okay, so we've heard this term before, I think, one-to-one. That's something that I remember from high school, so I'm pretty sure you've learned it already. So if function is one-to-one, we also call it injective. It's another word for that. It's just a fancier word because it's a Latin root. We love our Latin roots in math. It's one-to-one or injective if whenever you have different elements of your domain, you have different elements of the range. You have different outputs, okay? Different elements of the domain are mapped to different outputs, okay? So F maps different elements in X to different elements in Y, okay? So it's weird because you have kind of a negation going on, but it will make sense, okay, I promise. So informally, that's probably the way that you want to think about it, is F never hits the same place twice, yeah? So here's a function. Let me draw my domain and my target. So let's write a function that is one-to-one using arrows. Okay, so let's see here. Dun dun dun. We got to go like this. Maybe we'll have 4. Why not? So we can do this. I can do my original example, right? Bam. That is a one-to-one function because any x that is different is being mapped to a different y. Yeah? F is not hitting the same place twice over here. Okay, so a good example of a function that is not one-to-one is this. I could pick the same range if I wanted to, but I want to show you a problem. If I had two elements to map to only, if this was my codomain and this were my domain, it is impossible for this function to be one-to-one. It's impossible for it to be injective because I got to take this somewhere. I got to take this somewhere, and now I have to take this somewhere too. See that? You're forced. So it can't be one-to-one if the target is smaller. This one had some room. We could have added a fourth element. Okay. So it tells you something. This tells you something about the size of your target. Interesting. We'll talk about that later, maybe. Okay, so this is not one-to-one because both of these are being mapped to right here, and we don't like that. Okay, so this is bad. We don't like that at all. Okay, so that is why it is not one-to-one. It is hitting the same place. X1 is unequal to X2, so like let's pretend this is A, B, and C. So yeah, B is unequal to C, but f of B is equal. F of B is equal to f of C. Sad face. Okay? Alright, so that is one-to-one / injective. And now we have onto or surjective. So another Latin root we like to use. So these are interchangeable, onto or surjective. So a function, f to y, is called onto if the range is equal to the target. Okay? So this is why we have to have two terms, because sometimes it's not the same, but when it is, we have a nice word for it. Okay? We call it onto. So here's the mathematical way of describing that. For every y and y, so for every element of the target, there is an x. So for all first, then a there exists an x in x in the domain, such that f of x equals y. So informally again, f is hitting every element of the target, every element of the codomain. So here we go. A function that is onto, well, here's one. Doesn't necessarily have to be one-to-one either. Bam, bam. There we go. Oh, let's make this prettier. That's more like a function. Okay, so here's a function that is onto, because every element of the range is being, every element of the codomain is being hit. It is equal to the range. Okay, that is the idea. So hopefully that makes sense. And now, let me show you a function that is not onto. And this is kind of the dual to this problem. You are guaranteed to never get an onto function if the set that you're mapping to is bigger. Right? So if I only had 3 things to map, like they went here, there's always going to be an odd man out. You see that? The function cannot be onto if the domain is smaller. Okay? Or if you doubled up, like if this didn't exist and this went, like this one also went there or something, then you can also not have an onto function. But there are many different ways of doing this, but hopefully you see the problem. Onto or non-onto functions, it tells you something about the size of the domain sometimes. Okay, so that is one-to-one / injective and onto / surjective. Okay, more properties, and now we think of this as a nice thing to have. We think of this as a nice thing to have. What if we had both? Would that be even nicer? The answer is yes, of course. So a function that is both one-to-one and onto, we call bijective. Okay? So I don't know if there's a non-Latin way of saying this. It's something like maybe invertible is a good idea, a good way of saying it. But that's also a Latin root, isn't it? So a bijective function is called a bijection or a one-to-one correspondence. So not just one-to-one anymore, but also a correspondence. Cool, huh? So that is what it means to be a bijection. We are guaranteed, if we have a bijection, if f from x to y is a bijection, then we have to have an inverse. It's going to exist, okay, for reasons. And the inverse is, we write it as f to the -1 power, if we could do that. And it goes from y to x this time. You see that? It goes in the opposite direction. The domain and codomain swap. And here's how you can define the bijection. Sorry, here's how you can define the inverse, my bad. It's just you take every element of the original function and you just flip-flop them, okay? The domain becomes the codomain. The thing that was getting mapped to becomes the thing that's mapping, okay? And this is guaranteed to be well-defined because you're only ever mapping one thing somewhere else, okay? You're only ever mapping one thing to another place. That's what it means to be one-to-one. And then because it's onto, you're only getting mapped by, or you're getting mapped always somewhere. So you can always go backwards. You can always go backwards to where you came from. That's my hand-wavy idea. Okay? And there's only one place you could have come from. Okay, so here's a function that is bijective. Boop, boop, boop. And necessarily, these have to be the same size. Okay? They're required. So it's one-to-one because it's mapping everybody to a different place. Nobody's overlapping. And it's also onto because every element of the codomain is getting hit. So that means we can always follow this backwards. We can always redo these arrows. And we are guaranteed to have a function in this direction. You see that? It's beautiful. So that's our inverse. Okay? So this is our function f. Our inverse is the dotted line. Let me draw it like this. Let's pretend that this was the set x, this was the set y. So the inverse is yx, or we're going to have x and y in the same place, I guess. If only I could remember to do that. The arrows are just going in the opposite direction. That would probably be the easiest way for me to draw this. So instead of that way, we're going this way now. Where did you come from? Bam and bam. Okay, so that's the inverse. It exists. And as usual, we just swap the input and output, swap x and y. So I've kind of hinted at this, but what do you think, like what breaks down when the function isn't one-to-one? Why does that mean it can't have an inverse? And if it's not onto, but maybe it is one-to-one, why can it still not have an inverse? Okay, I want you to think about that. That will be very, very helpful for your homework and for any test. Okay, so a fun thing that I'm sure you've done in a math class before, but I want to just test you on, just to make sure we're all on the same page. Find the inverse of the following functions, if it is well defined. Maybe it's not, in which case, don't do it, okay? So, okay, we have A and B. Let's do this first one. Let's call this, let's just call them F and G so I can talk about both of them and we don't get confused. How about that? Okay, so for f, it's taking integers to integers, and it's taking one integer to that integer plus 3. And this is weird because all these things that I've been drawing, they are finite, right? They were finite sets, but now we're doing inverses of actual, like, infinite sets. What in the world is this going to even work? And, okay, let's think about this one. F of x equals x plus 3. Is that one-to-one? So if I can kind of, like, draw, I don't know, let's draw z up here, and another z over here. So the idea is it's taking, like, I don't know, -3 to 3. It's taking it's taking -3 to 0. That would be funny. -2 to 1, -1 to 2, etc., etc. And I think you can see that it is both one-to-one. It's only ever being hit. It's never doubling up. That's impossible. And also, it's going to hit everybody because you can always just go a bit farther back and find somebody that's going to map over here. Yeah? So that's totally invertible. What's the inverse? Well, if you think of this as like y, you just flip-flop them. You'd be like, okay, instead, just flip-flop f of x and x, and we can solve for f of x, okay? Dun, dun, dun. So, like, I don't know, what's the best way to do this? What's the right notation that I want to teach you? Well, let's flip-flop it. Let's make x this, x equals, and then we're going to replace this with the inverse. How about that? And if we just solve for f inverse of x, we will have found the function. Okay, so we just subtract 3 from both sides. So f inverse of x equals x minus 3. So if you wanted to know how you came from here, just subtract 3. Yeah? And so that is the inverse. Boop. So that's the first one. And okay, then now let's do it for g. So is this invertible? And I have a feeling it's not doubling up. Like it's 1-to-1. If we draw this, it's a line, right? We can draw as many lines as we want. We don't hit two things. And I think, given enough time, if it looks like a line, it's going to hit eventually every y value. Yeah? I think that's possible. So I'm pretty sure this is invertible, and we can solve for the inverse. So we're going to flip-flop now the difference. Okay, so we're going to replace x and g of x. So g of x becomes x, and then it's 2, and I guess we could write g of x, but I prefer to write g inverse of x to talk about what we're doing here. 2 times g inverse of x plus 34, and we just solve for g inverse of x now. So, okay, so that means x minus 34 equals 2 g inverse of x, and then g inverse of x is therefore equal to x minus 34 over 2. Oh, wait a second. Is this well defined? This is even possible. I'm not sure about that. Because, okay, this would be the inverse if it existed. But I think I can give you an x for which it's impossible, right? Let's give 35. Let's let g of 35 exist, okay? G inverse of 35 would have to be, it would have to be 35 minus 34 over 2. You see where I'm going with this? Equals 1/2. Wait, but that's not an integer. Oh no. So we're not actually getting mapped to 35, okay? So our intuition with this graph was completely wrong, and we can spell this out. Like, we can go to, let's do, gosh, I don't know, g of 0, that equals 34, and then g of 1, what's that? Oh, that's 36. We just skipped 35. So we're not hitting everybody. It is not invertible, okay? G is not invertible. Okay, so it's a little bit of a trick. Did you see that? Whee. Okay, so, yeah, that was the inverse. And let's see here. Let's get through these. So composing functions now. This I think you've seen before as well. Gcomposed with f. It's a weird notation, but it works. So what it is, it's a way of combining functions. It's making a third function out of two functions, yeah? It makes a brand new function. Gcomposed with f, what it means is first do f, then do g, yeah? You can read it as g after f. A lot of math professors sometimes like to read it like that. G after f to make it clear that you're doing f first, right? So, okay, here's an example. F maps integers to natural numbers because this is the absolute value function. So this is like, remember I was giving you an absolute value function before. It was mapping z to z, I said. But a more restrictive codomain would be the natural numbers. Yeah? Same function though. So f maps a number to its absolute value, and integers to its absolute value, and g maps a natural number to true or false. So let's see here. And g of x is this function right here. So, hey, it's kind of like computer science now. Is x greater than 2? Okay? So, let's talk about the composition of g with f. So, g after f of -5 is this. Okay, this is how you write it. You do f first. Do f first to -5. So do that, and then apply g to that result. Okay, hopefully this is coming back to us all. apply g to the result of f of -5. So it's kind of like you just replace this with a parenthesis, okay? And like get rid of that one. All right, so that becomes g of 5 because you take the absolute value of, that was what f did, took the absolute value. So now we're doing g of 5, and that is true. Yeah, so that is a composition of functions. And I want to stress that you have to have them match, okay? So if f is from z to n, and g is from n to true false, and you want to compose, these better be the same. Boop and boop. Those must be equal. Okay? That is a requirement for function composition to happen. If that's not true, it doesn't happen. Okay? So that is that. Let's do maybe these first two. Gcomposed with f is, let's see here, first do f, then do g, and I'm just asking for the types. Okay, what is it going to be? So first you do, like if we were talking about these, first you did f, we gave it an integer, we got a natural number. Then we composed it with g, so we gave that a natural number, and it finally gave us true to false. So when you compose them, you take the same thing as the first function. You take the same element as its domain. We took an integer, but we give back the element of the second function, the element of the second function's codomain. Okay? So you kind of like get rid of these things right here. Yeah? They kind of like meld away. All right, so if we're going to compose g after f here, we're going to first do f, so it's going to take an a, guaranteed to take an a, but then f gives us back a b, and then we immediately apply g to that b, so we take the b and then we get back a c, okay? So if we were to do g composed with f here, we would get back a c. We would go from a to c, that is the new function that it makes. Okay, you see how that is getting rid of this intermediate thing? Okay, how about this one? First we do g, so we took a b, and then we get back a c, and then we apply f to that. Oh, we can't apply it to an a. We have a c, we're trying to apply a function that needs an a. No, that's not going to work. Dun dun dun. So not defined. The composition is not defined there. Okay, so that is composition. I think I would like to stop now, and we're going to come back and talk about the identity function in the next lecture. Okay, and we'll do some examples with that. So the composition, just remember, it's not guaranteed to always exist. Okay, these need to match up, and if they don't, then we don't have a composition. Okay, so I'm going to see you in the next lecture, and then we will continue from here.